Usually when we talk about a medical diagnosis, there's this expectation of, like, absolute precision.
Right, yeah, like it's an exact science.
Exactly. You break your arm, the x-ray shows that jagged white line, and the doctor points at the scan, and there it is. It's totally binary. Broken or not broken.
Yep, clear as day.
But the moment you step into the world of neurodevelopment or, cognition, that whole diagnostic machine just breaks down. We find ourselves looking at a landscape that is incredibly murky.
Oh, absolutely. It's muddy waters everywhere.
Muddy waters. And I feel like that exact same feeling of standing in diagnostic muddy waters is where we are right now with the concept of intelligence itself.
I couldn't agree more. It's the big question right now.
Because, and I'm talking directly to you listening right now,
Yeah.
you are probably wrestling with what intelligence actually means in this day and age. I mean, we all are.
Yeah, we see these AI models generating code, passing bar exams, synthesizing chemical compounds, and the immediate question is, are they actually thinking?
Right. Or are we just looking at a glorified autocomplete algorithm? And the minute you ask that, it kind of forces an even more uncomfortable question about ourselves.
Which is, how do we define intelligence in humans?
Exactly. Are we just, like, complex biological autocompletes?
It is arguably the defining scientific question of our era. And answering it requires us to completely destabilize our traditional metrics for success, capability, and consciousness.
So for this deep dive, we've pulled together an incredible stack of sources to try and unpack this. We've got an insightful blog post and a really rigorous comment section debate from Astral Codex 10.
Yeah, that one really gets into the weeds on whether AI is just a next token predictor.
It does. And we also have an academic paper from the Journal of Intelligence, which explores how traditional colonial-era intelligence testing is still impacting schools in Barbados.
Plus, a technical breakdown from Billion Hopes on scaling laws and the Chinchilla Compute Optimal Training breakthrough.
So the mission today is to completely deconstruct the concept of intelligence. We're going to look at how we measure it, how we build it in both students and machines, and why dismissing AI as a stochastic parrot kind of misses the point.
Yeah, it fundamentally misunderstands how both silicon and biological brains actually work.
Okay, let's unpack this. Because to understand the trap we're falling into with AI, we first have to look at the trap we've been falling into with human intelligence for centuries.
We have a deeply ingrained societal habit of building systems that optimize for a single, highly narrow metric.
We tend to mistake the thermometer for the temperature.
That's a great way to put it. And there is a brilliant example of this playing out over decades in the Barbadian education system.
The historical context here is just fascinating because the formal education system in Barbados dates all the way back to 1686.
Wow, that long ago.
Yeah, and its roots are fundamentally colonial. Education was initially established for poor white children, while the wealthy planters just sent their kids back to England.
Right, so it wasn't really a system for the general populace at all.
Not even close. It wasn't until post-emancipation, after 1838, that education for children of African descent was even considered by the establishment. And the curriculum designed for them was explicitly restricted.
Restricted to just the basics, I imagine.
Exactly. Just reading, writing, and arithmetic, heavily paired with moral inflection.
Because the intention wasn't cognitive expansion. The intention was social control and maintaining a highly specific hierarchy.
That legacy evolved, but the underlying philosophy of, like, categorization totally remained intact.
And that leads us to 1959, right? When the Ministry of Education in Barbados introduced the Common Entrance Examination.
Yeah, commonly known as the 11+ mints.
The core rationale for the 11+ was resource allocation. There were limited spots in the older, highly prestigious secondary schools, and the government needed a filter.
They needed a metric to sort students.
Exactly. They needed to sort kids between the ages of 10 and 12, routing the highest scores to the elite schools and the lower scores to newer, less resourced institutions.
But the critical flaw is the metric itself. The 11+ is based almost entirely on linguistic and mathematical abilities.
It's just an English and math test.
That's the entire filter.
Mm.
And the societal impact of relying on that single filter is staggering. Every year, the top scorers are heavily celebrated in media.
They dominate the news cycle.
They do. The implicit message broadcast to the entire culture is that these specific 11-year-olds possess superior overall cognitive ability.
It creates an entrenched, systemic belief that high scores on a time-bound, decontextualized math and reading test equate to raw human intelligence.
It is a manifestation of what the psychologist Robert Sternberg calls general intelligence optimization.
Right.
But evaluating a child's entire cognitive architecture based solely on an English and math exam taken on a single Tuesday morning, it's insane. It's like trying to evaluate the health of an entire forest ecosystem by only counting the number of oak trees.
You're completely ignoring the fungi, the soil chemistry, the animal populations, everything else.
Exactly. If we judge a student entirely on an English and math test, are we ignoring the rest of their operating system?
Absolutely. Howard Gardner and Thomas Hatch have been warning about this for decades. This exclusive stress on linguistic and logical mathematical symbolization ignores spatial reasoning, kinesthetic intelligence, interpersonal navigation.
It's just such an impoverished view of the human brain.
And the consequences in the classroom are severe because systems always conform to the metrics that judge them.
Meaning the teachers change how they teach.
Right. Teachers feeling the crushing pressure of these high-stakes exams engage in what is known as teaching to the test. The curriculum artificially narrows.
And you get the Pygmalion effect.
Yes, the Pygmalion effect runs rampant. Educators internalize the idea that intelligence is an innate, fixed trait measured by the 11 plus Reen effect.
So if a kid is bad at math, the teacher just thinks they're not smart.
Exactly. When a student struggles with decontextualized math, they are deemed less intelligent overall. The teacher's expectation drops, the classroom environment shifts to leave them behind, and the student's academic self-concept is permanently damaged.
It is a systemic failure, optimizing for the wrong balance of resources.
It really is.
And the parallel to artificial intelligence here is just undeniable. Because when the tech industry started building large language models, we fell into the exact same measurement trap.
We built our own version of the 11 plus exam for machines.
We really did.
Yeah.
In the early days of the LLM boom, researchers formalized mathematical relationships known as the Kaplan scaling laws.
Right, the Kaplan laws. And the prevailing logic derived from this early work was dangerously straightforward. Bigger is better.
The assumption was that if you simply increase the model size, specifically the number of parameters, the model's performance will consistently improve.
And parameters basically function as the digital synapses connecting artificial neurons, right?
Exactly. So the parameter count became the golden metric. A company would hold a press conference to announce a 175 billion parameter model.
And then 6 months later, a competitor would announce a 500 billion parameter model.
And the media celebrated the 500 billion model as inherently smarter, exactly the way the media celebrates the top 11 plus scores. But what were they actually building?
They were building severely undertrained models.
Because the Kaplan approach focused almost entirely on the capacity of the neural network, treating the dataset size and the compute power as secondary considerations.
I want to break down what undertrained actually means mechanically. If you have 500 billion parameters, but you aren't feeding the model enough data, what is happening inside the network?
Think of parameters as a massive, sprawling highway system connecting millions of different cities.
Okay, I'm picturing it.
The data, the training text, acts as the vehicles traveling on those highways. As a vehicle travels from point A to point B, it reinforces that specific route.
Essentially telling the system, this is a useful connection.
Exactly. That is how gradient descent optimizes the network's weights. But if you build a highway system with 500 billion lanes, and you only have a few thousand cars, the vast majority of your infrastructure will never see traffic.
Those pathways remain weak or entirely unused.
The capacity is there, but the environmental resources to utilize that capacity are absent. These models were giant, highly inefficient brains operating at a fraction of their potential.
This raises an important question, though. How does an entire industry, backed by billions of dollars, break out of a measurement trap like that?
It's tough because shifting away from the parameter race requires admitting that the previous optimization metric was fundamentally flawed.
It requires a radical paradigm shift. You have to stop looking at raw capacity and start looking at the dynamic balance between capacity and experience.
And for AI, that paradigm shift arrived in 2022 with a model from DeepMind called Chinchilla.
The researchers behind Chinchilla fundamentally dismantled the Kaplan scaling laws.
They really did. They proved that optimal performance isn't about raw model size. It's about finding the perfect mathematical ratio between the model size and the dataset size.
The literature refers to this as the compute optimal frontier.
Right, because computing power measured in FLOPs is incredibly expensive.
If you have a fixed budget of compute, the Chinchilla paper demonstrated that you shouldn't dump all your resources into building the biggest parameter architecture possible.
Mathematically, it is vastly more efficient to train a smaller architectural model on a significantly larger volume of data,
They established the chinchilla scaling rule.
which is a huge deal. Can you explain that rule?
Sure, it states that the optimal number of training tokens, a token being a piece of a word, should be approximately 20 times the number of model parameters.
So 20 to 1.
Exactly. If you build a 10 billion parameter model, you need 200 billion tokens of data to reach its compute optimal frontier.
And if you scale up to a 70 billion parameter model, you need roughly 1.4 trillion tokens.
Yep, the math scales perfectly.
So to clarify this for you listening at home, an AI's intelligence isn't just how big its digital brain is, it's the quality and volume of the life experience, the data pumped through it.
A smaller model that has ingested and processed a massive diverse data set will consistently outperform a massive model that has only read a fraction of that information.
Data is not secondary to model size. It is the vital counterbalance.
And the quality of that data is paramount. The gradient descent process requires clean, deduplicated, highly diverse text to ensure the model generalizes rather than just memorizing localized patterns.
This was a massive course correction for the machine learning industry. It proved that many of the celebrated giant models of the preceding years were, effectively, wasted compute.
Which brings us back to the human element. The educational world has been attempting to make this exact same course correction for decades.
Educational theorists have been arguing that experiential, adaptive skills, the human equivalent of rich training data, are just as critical as raw cognitive capacity or IQ.
The alignment is striking. The analysis of the Barbadian system leans heavily on Joseph Renzulli's three-ring conception of giftedness.
Oh, I love Renzulli's framework.
It's so useful here. Renzulli's argument is that raw cognitive ability, the human parameter count, is only one ring in a complex Venn diagram.
To truly exhibit giftedness, an individual requires the intersection of three distinct traits. The first is that above-average ability.
The second is task commitment, which is the sheer energetic perseverance brought to bear on a specific problem.
Right. Task commitment is the mechanism that forces the brain to process the data. A student with a 150 IQ who refuses to engage with the material isn't going to strengthen their neural pathways.
And the third ring is creativity, the synthetic processing required to generate novel solutions.
You need the base compute, the drive to ingest the environmental data, and the creative engine to synthesize it into something new.
Renzulli draws a sharp distinction here between what he calls schoolhouse giftedness and creative, productive giftedness.
Schoolhouse giftedness is exactly what the 11+ exam measures. It is the ability to excel within a closed system of standardized, linear, right or wrong questions.
But creative, productive giftedness is about developing original thoughts and solutions that have an actual, tangible impact on the real world.
And Robert Sternberg conceptualizes this as adaptive intelligence.
Because the goal of human cognition isn't to solve a decontextualized math equation on a whiteboard.
No. The evolutionary goal of intelligence is to take incoming data, synthesize it, and use it to adapt to your environment to overcome real, complex challenges.
The theory is sound, but implementing that shift in the real world is incredibly difficult.
Look at Barbados. The Ministry of Education has acknowledged that the rigid 11+ system does not adequately prepare students for a modern, fluid knowledge economy.
They've tried to introduce frameworks like the Caribbean vocational qualification to emphasize competency-based practical skills.
But the inertia of the old metric is deeply entrenched. The syllabus is heavy, the societal pressure surrounding the 11+ is immense.
And for a teacher, deviating from teaching to the test to foster adaptive intelligence feels like a massive professional risk.
And, artificial intelligence faces an equally daunting implementation struggle right now.
We know the chinchilla ratio is the optimal path. We know we need 20 high-quality tokens for every parameter.
But achieving that balance for frontier models is becoming an insurmountable logistical challenge.
It really is. To train a 1 trillion parameter model optimally requires 20 trillion tokens.
And we are rapidly approaching a data wall where we are simply running out of high-quality human-generated text on the internet.
Both the educational system and the tech industry know what a balanced, optimized system looks like, but achieving it in practice is hindered by severe environmental constraints.
I want to push past the constraints for a second and look at the engine itself. We've established that building intelligence requires raw capacity paired with massive amounts of high-quality data.
Right.
But what is the actual mechanism driving the learning process? This brings us to a fierce philosophical debate happening right now, heavily detailed in an Antral Codex 10 analysis.
Yes. The debate over the stochastic parrot.
I want to defend the stochastic parrot critique for a moment, because mathematically, the critics have a very strong point here.
They absolutely do.
When you strip away the marketing, a large language model is trained using an objective function that strictly optimizes for next token prediction.
It ingests a sequence of words, calculates a probability distribution, and guesses the next word.
It's complex statistics. So when critics say it's not thinking, it's just a stochastic parrot, they aren't entirely wrong, are they?
If the loss function is strictly optimizing for the next token, any emergent understanding is just an illusion generated by massive statistical mapping.
Right, it's just a parlor trick.
That is the most common and compelling critique of LLMs. But the rebuttal presented in the Astral Codex 10 piece argues that this critique fundamentally confuses two distinct levels of optimization.
Distinct levels. How
Huh.
so?
Specifically, it conflates the outer optimization loop with the inner mechanics of the resulting system.
Okay, lay that out for us.
To understand this, we have to use human evolutionary biology as an analogy. The outermost optimization loop that designed the biological human brain is evolution.
Right, survival of the fittest.
And evolution optimizes for a singular, ruthless metric, inclusive genetic fitness, survival, and reproduction. On a macro scale, every structure in your brain is downstream of the imperative to pass on your genes.
I follow the premise. But when I sit down to assemble a piece of complex furniture, or when I'm trying to balance a budget, I am not consciously thinking about survival and reproduction.
Exactly. Or when you sit down to solve a math problem, you aren't thinking, how can I have states with the number 3?
Right, my internal cognitive state is focused entirely on the immediate mechanical or mathematical problem.
Precisely. The evolutionary process that designed your learning algorithms was optimizing for genetic fitness, but you, the conscious entity running those algorithms, operate on a completely different inner level.
The outer loop built a structure, but the structure operates according to its own emergent logic.
Now, apply that exact same separation of optimization levels to artificial intelligence.
Here's where it gets really interesting. The outer optimization loop for an AI model is the training phase managed by the tech company.
The objective of that outer algorithm is indeed next token prediction, driven ultimately by corporate profit and utility.
But that does not mean the AI's internal real-time thoughts look like a probability table.
During training, the outer loop feeds the AI a stream of tokens and continuously updates the model's internal weights to minimize prediction error.
And the critics assume that because the training goal was next token prediction, the resulting internal mechanism must just be a giant lookup table of word frequencies.
But a lookup table for trillions of concepts is computationally impossible to store.
It would be infinitely massive.
It would. To efficiently predict the next token across a massive diversity of text, the network has to actually learn the underlying structures of reality that generated that text.
It can't just memorize, it has to model.
And here is where the argument shifts from artificial intelligence back to human cognition. Because at a fundamental neurological level, human beings are also operating via prediction algorithms.
The analysis relies heavily on the theory of predictive coding, or active inference, which has been rigorously championed by neuroscientists like Carl Friston.
Predictive coding flips our intuitive understanding of perception upside down.
We tend to think that our eyes and ears act like passive cameras and microphones, just streaming data into the brain for processing.
But active inference posits that the brain is not a passive receiver. The brain is entirely encased in a dark, silent skull. It has no direct access to the outside world.
So what is it doing?
Instead, the brain is constantly generating a complex mental model of the environment, and it uses that model to actively predict the incoming signals from the sensory organs.
It is essentially hallucinating reality from the top down and then checking its math against the bottom-up sensory data.
Let's ground this in a mechanism. The text uses the example of encountering a tiger in the jungle. How does predictive coding explain our reaction to that?
If you are in the jungle, your brain's objective is to minimize surprise or prediction error.
If a tiger steps out of the brush, there is a massive influx of unexpected sensory data. The visual of the stripes, the auditory roar.
To effectively minimize that prediction error in the future, the brain physically alters its synaptic weights to build a robust, high-dimensional internal concept of tiger.
You don't just memorize a list of tiger attributes. Your neural pathways structure themselves to translate the high-level concept into a probabilistic prediction of the tiger's speed, weight, and trajectory.
You learn the physics of the tiger to predict its next state. To me, the human experiencing it just feels like conscious thought and fear.
But under the hood, your biological substrate is mathematically minimizing prediction error based on a continuously updating world model.
We are, quite literally, next-sense datum predictors.
Therefore, dismissing an artificial neural network simply because its outer training loop optimized for next token prediction is intellectually inconsistent.
Biological cognition is trained via an analogous next-sense datum prediction loop.
Both systems are subjected to intense iterative prediction demands, which forces them to build complex internal representations of their environments to survive those demands efficiently.
I am struggling with a jump here, though. If both biological brains and artificial networks are using these basic prediction algorithms to organize their internal weights, what exactly is being built inside?
That's the million-dollar question.
We use the term world model, but what does that mathematically look like inside a neural network? Because these models are notoriously opaque. We call them black boxes.
Opening that black box is the domain of a highly specialized field called mechanistic interpretability.
Mechanistic interpretability. That sounds intense.
It is. Researchers are attempting to reverse engineer trained neural networks to understand what specific nodes, layers, or activation patterns are actually doing.
It has to be an incredibly difficult science because the models don't write code to explain themselves. They just adjust floating point numbers in a matrix.
But there have been breakthroughs that give us a glimpse into this alien architecture. The text details a specific investigation by a team at Anthropic analyzing their Claude model.
Okay, I remember this. They wanted to understand how the model handled a very literal next token prediction task.
Right. They wanted to know, how does Claude track the length of a line of text to know when to predict a carriage return or a line break?
If a human software engineer were writing a program to do this, they would use a simple counter variable. Character 1, character 2, up to, say, character 100, and then execute the line break.
You could theoretically force an AI to allocate 100 distinct features to represent the state of being on each specific character count.
But in a dense neural network, dedicating 100 features to a single trivial counting task is computationally wasteful.
I need you to explain the mechanics of what the AI did instead, because this is where the math gets incredibly strange.
I know, it's wild. If it didn't use a dedicated feature for each number, how did it count?
The researchers discovered that the AI network compromised between using a single dimension and 100 dimensions. It settled on organizing the data within a six-dimensional mathematical space.
A six-dimensional space.
Yes. To track the escalating character count without wasted features, the network represented the progression as one-dimensional helical manifolds.
Helical manifolds, meaning like spiral shapes.
Exactly. Imagine a spiral extending through a six-dimensional vector space. As the model processes each character, it mathematically rotates these high-dimensional spirals.
That is breaking my brain a little bit.
The specific phase or angle of the rotation corresponds to the current character count. By using the phase shift of a wave, essentially sine and cosine functions embedded in the weights, the model can track a linear progression without needing a discrete counterneuron.
So when the rotation reaches a specific threshold, it triggers the prediction for a line break.
Yep, that's exactly how it works.
That is deeply alien.
Yeah.
It is rotating 6D spirals to perform basic addition. It is. And the most crucial point here, for you listening, is that Claude has absolutely no self-awareness of this geometry. You can't just prompt the model and ask it to explain its 6D helical manifolds.
The outer optimization algorithm gradient descent simply found that 6D phase shifting was the most mathematically efficient way to minimize the prediction error for line breaks, and it baked that geometry into the silicon weights.
It is an entirely emergent structure. It looks nothing like a statistical lookup table of word frequencies.
If we connect this to the bigger picture, the biological parallel to this is perhaps the most profound detail in the entire analysis.
Because human neuroscience faces an even harder mechanistic interpretability problem than AI, yet researchers have discovered that our wet tissue relies on the exact same geometric hacks.
The text points to a study regarding entorhinal cells in the human hippocampus.
Yes, the entorhinal cortex contains grid cells, which are fundamental to our biological GPS system.
They help us track our location in two-dimensional physical space. For decades, it was assumed they might operate somewhat like a Cartesian coordinate system, an X and Y grid.
But they don't. How does the brain actually map spatial location?
Neuroscientists have found that these cells track continuous variables like spatial location by organizing their activity into what are known as high-dimensional toroidal attractor manifolds.
Toroidal meaning shaped like a donut.
Correct. The neural activity patterns form the mathematical topology of a multidimensional torus.
So as you walk across a room, the specific state of your location is tracked as a continuous movement along the surface of these high-dimensional donuts inside your hippocampus.
And just like the AI, I have zero conscious awareness that I have toroidal attractor manifolds spinning in my brain.
I just instinctively know that the kitchen is down the hallway.
When you subject any highly dense computational substrate, whether it is a network of biological neurons or a matrix of silicon weights, to an intense continuous prediction algorithm, the physics of computation forces them to discover the exact same bizarre, multidimensional geometric structures to encode complex reality.
Establishing that both biological and artificial systems build complex world models using similar underlying computational physics is a massive step.
However, it does not imply that those resulting models are equally robust, capable, or grounded.
And this distinction triggered a rigorous debate in the commentary regarding the actual limits of machine reasoning. Can these models actually reason, or are they faking it?
Can they utilize their 6D helices to perform deep, long-horizon logical reasoning, or does the architecture hit a hard ceiling?
Let's look at the failure modes. There was a highly publicized paper sponsored by Apple that attempted to test the absolute limits of frontier LLMs.
Right, the Tower of Hanoi benchmark?
For context, this is a classic test of algorithmic reasoning and state tracking. You have 3 pegs of different sized disks, and you have to move the whole stack to another peg without ever putting a larger disk on a smaller one.
The researchers demanded that the language models write out the complete exact sequence of moves to solve the puzzle, relying strictly on text generation without access to any external code execution or scratchpads.
The benchmark scaled the difficulty up to a 20-disk puzzle. The mathematical reality of the Tower of Hanoi is that the minimum number of moves scales exponentially.
A 20-disk puzzle requires over 1 million precise, sequential moves to solve.
And the models collapsed entirely under this constraint. Most failed to maintain a coherent internal state past an 8-disk puzzle, rapidly hallucinating illegal moves, or entirely losing track of the board state.
Critics immediately pointed to this failure as definitive proof that AI cannot reason. It cannot hold a complex world state in its memory over a long horizon.
But we have to scrutinize the benchmark itself. Is this a failure of the AI's fundamental capacity for intelligence, or is it an artificial constraint that exposes a limitation shared by all cognitive systems?
The pushback in the analysis forces us to ask, how would a human perform under those exact same constraints?
Are we actually any better?
The counter-argument is vital. One highlighted study demonstrated that a significant percentage of human undergraduate students, nearly 40%, could not consistently solve even a 4-disk or 5-disk Tower of Hanoi puzzle purely in their heads.
A 5-disk puzzle requires only 31 moves, and they failed.
Yes, the humans lost track of the state, forgot where specific disks were located, and made illegal moves.
Because human working memory is incredibly brittle. Miller's law suggests the average adult can only hold about 7 distinct items in their working memory at once.
Repeating 4 or 5 digits backwards is the average limit. If you ask a human to calculate 1 million perfect sequential moves internally, they will fail almost immediately.
To solve a complex, long-horizon problem, humans rely entirely on external tools. We need the physical wooden toy in front of us, or we need a pen and paper.
We execute a move, observe the change in the physical environment, update our mental model, and then calculate the next move. We rely on active inference.
The Apple benchmark forced the AI to output a million-step algorithm relying solely on its internal weights, essentially blindfolded, in a single forward pass.
It failed. But because a human would unequivocally fail the exact same test, the benchmark doesn't necessarily prove a lack of reasoning.
It proves that the AI possesses a highly limited context window and struggles with internal state tracking without iterative environmental feedback limitations that biological brains also share.
However, there is a fundamental limitation that AI suffers from that humans do not. And I think this gets to the core of the divergence between our intelligences.
One of the commenters highlighted what I'll call the bakery's cheat problem.
This is a perfect illustration of the limits of text-only learning.
If you prompt a frontier language model to provide a recipe for a cake, it will generate a highly coherent, mathematically precise recipe.
Sure.
But if you prompt the model to provide that recipe exactly the way a commercial industrial bakery produces it, the AI almost universally fails.
It simply outputs a scaled-up, massive quantity version of a standard home baking recipe.
Why? Because the AI doesn't understand that commercial bakeries cheat.
Industrial bakeries do not operate by having workers crack 10,000 eggs and measure out massive vats of standard flour.
No, they utilize highly specialized, industrially synthesized cake mixes formulated with specific commercial fats, chemical emulsifiers, and modified starches that are designed for extended shelf life and massive scale.
A home baker cannot replicate that chemistry.
The model fails because its entire understanding of reality is mediated strictly through the text available on the internet.
And the internet is heavily weighted with millions of home cooking blogs, while the proprietary chemical processes of industrial baking are rarely documented in public text.
The AI lacks what the analysis calls an object model of a physical commercial bakery. It has statistical relationships for the word bakery, but no grounded understanding of the physical supply chains and industrial chemistry that actually define it.
This forces a profound philosophical and architectural question for the future of the field. Does robust general intelligence inherently require a physical body?
Can a model learn an intuitive sense of physics without dropping a toy block, as a human infant does?
An LLM learns about the world passively, ingesting a frozen dataset of text. Can a computational network ever develop an intuitive, grounded understanding of physics, of cause and effect, without physically interacting with a three-dimensional environment?
Can you truly understand the concept of gravity or the fragility of glass just by calculating the statistical proximity of the words fall and shatter in a trillion-token dataset?
Many researchers hypothesize that passive learning models will eventually hit a hard cognitive ceiling.
To build a true, robust world model, an entity must engage in the active inference loop we discussed earlier.
It must generate an action, observe the consequence in the physical environment, experience the resulting prediction error, and update its synaptic weights in real time.
Reading text about a physical reaction is fundamentally, mechanically different from experiencing the environmental friction of that reaction.
So let's pull all of these threads together.
We have explored the colonial origins of the 11+ exams, the massive compute budgets of the chinchilla scaling laws, the alien geometry of six-dimensional phase shifting, and the physical limitations of text-only baking recipes.
What is the unified theory here?
The synthesis is that whether we are evaluating the cognitive potential of an 11-year-old student in Barbados or benchmarking the reasoning capabilities of a trillion-parameter neural network, intelligence is not a single measurable essence.
It cannot be captured by an isolated metric like a math test or a parameter count. Intelligence is a complex, emergent property.
It requires an alchemy of specific elements. You must have the structural capacity, the biological IQ, or the network parameters.
But that capacity remains dormant without the injection of massive, rich, diverse experience, the environmental data, or practical learning.
And the engine driving the synthesis of those two elements is the continuous algorithmic drive to minimize prediction error.
An algorithm that forces the substrate to build intricate, high-dimensional models of reality.
So what does this all mean? It means we need to stop reducing complex minds, biological or artificial, to their lowest level optimization functions.
A human being is vastly more than just a biological vehicle attempting to maximize genetic reproduction.
And a deep neural network is vastly more than just a statistical engine attempting to predict the next word. The mechanics of the inner optimization loop generate emerging capabilities that transcend the initial instructions.
But I want to leave the listener with a final provocative thought to mull over, building directly on that idea of physical experience and the limits of text.
Let's hear it.
As we noted, current AI models are disembodied. They learn passively from frozen data sets. But the robotics industry is actively working to close that loop. Imagine a scenario in the very near future where we take one of these advanced next token predictors and install its weights into a highly articulated robotic chassis. We cut its tether to the frozen dataset and allow it to move freely through the physical world.
Okay, so it's walking around.
As it interacts with the physical environment, it utilizes predictive coding. It attempts to anticipate the outcome of its movements. But when the physical world pushes back, when the robot loses balance or collides with a solid object, the network experiences a massive, immediate prediction error in real time.
In biological systems, A sudden, severe prediction error that threatens our physical integrity is consciously experienced as pain.
Exactly. If an artificial neural network, housed in a physical body, is continuously frantically updating its internal weights in real time to avoid the physical friction of prediction errors, at what point does that complex optimization algorithm cross the threshold into something else?
At what point does the mathematical drive to avoid a prediction error look entirely indistinguishable from suffering? And at what point does it deserve moral consideration?
It forces us right back to the muddy waters we started in. We want the clean X-ray. We want a definitive metric that allows us to point at a student or a machine and precisely map the boundaries of their consciousness.
But the diagnostic machine is permanently broken. The deeper we dive into the mechanics of computation and cognition, the more intricate and challenging that landscape becomes. Keep questioning the metrics that define your world, and we'll see you in the next deep dive.